So, as you can see, we are making our way through particle motion. We have talked about the five commandments of particle motion. And if you missed that video, it is one I think you definitely need to see. So, I'll link it in the description below. But today, and on this video, I want to look at finding the net and the total distance as it applies to the AP Calculus AB exam. So, let's jump right in. We are given the graph of the velocity. I think it's very important to always identify which graph you're looking at because it's going to make a difference in how you interpret the questions. The velocity is being measured in meters per second, and the object's moving along the x-axis. So this is asking me what values of t does the particle not have an acceleration, no acceleration. So friends, what this is asking me to is where is A of t undefined? Now, if I'm looking at the velocity graph, then the acceleration would be the derivative. So really what I'm asking you is look at this graph, tell me where the derivative does not exist. That would be at t equals 1 and 3 and 6 and 8. The acceleration is undefined. Well, if I can spell today, is undefined because V of t has cusps or sharp turns All right. Now, the next part wants us to identify or express the acceleration as a piecewise function. So remember, the acceleration is the derivative here. We want to write a piecewise function for the derivative. So we're going to take this in pieces because I see these line segments. That's really what we're working from. So let's write for the first piece. It's from 0 to 1. And we're doing the slope. Remember, just the slope because we're doing the derivative. That slope would be 3 over 1. Let's do the next piece from 1 to 3. And the slope here is down 3, right 1. That slope would be -3. Friends, I'm doing rise over run. Here's what I'm doing. The next piece would be from 3 to 6. And that slope would be 0. And then I'm going to go from 6 to 8. And that slope would be up 3, right 1. And then I'm going to go from 8 to 10. And that slope would be down 3, right 2. Check that again. That's down 3, right 2. So that's -3 halves. And so that's how I write. This is the velocity graph. So I'm writing an expression for the acceleration. That's the slopes. And I'm doing it in piecewise because of all the pieces that are involved here. Look at the next question. For what values of t is the particle moving right? So we know particles move right when the velocity is positive. This is the velocity graph. So when you're asking me about the velocity, I'm looking at the y values here. The particle moves right on, let's see, it's going to move right from 0 to 2 because those values are positive. Remember, I'm looking at the y values because I'm looking at the velocity. And from 7 to 10. And because I need to justify my answer, we're going to say because velocity is positive. So where is the object moving left? The particle moves left when the velocity, when the y values are negative. So that's between 2 and 7. All right, now look at the last question from this part. Find the average velocity from 1 to 8. Now, when you see the word average, that tends to mean that we should not use calculus. We should use algebra instead. So if I want to find the average acceleration, then I'm going to find the difference in the velocity over the difference in time. Remember, y2 minus y1. Now, you are looking at the velocity graph, and I know I keep saying that, but it is something you have to keep reminding yourself what it is you're looking at so you know if you should take the slope or you should look at the y value. Okay, so go to your graph and let's find the y value at 8. The y value at 8 is 3. Then you go find the y value at 1, which is also 3. And then 7 minus 8, I'm sorry, 8 minus 1 is 7. So I'm getting an average acceleration of 0 there. So let's turn our attention then to the net distance and total distance. I want us to kind of get a feel for how the two of these are similar and how they are different. Now, you probably are going to have to pause this video so that you can get all these definitions, these notes down because I won't be like pausing to write them all. So just hit the pause button and get them copied down, and then you can focus on the explanation. So when we talk about the net distance, we're talking about the distance from the starting point to the ending point. That is simply going to be subtract the starting point minus the ending point, or subtract the ending point minus the starting point. You can look at it in either way. Total distance, however, means something else. Total distance means the sum of all the distances moved. So if the particle stays moving in the same direction the whole time, we know that the net distance will equal the total distance. That doesn't always happen, of course, but if the particle never changes direction, then you can simply find the net distance would be the same as the total distance. How do we find that net distance? Like I said, starting point minus ending point. Why did I put the absolute values around it? Because a distance does not have direction with it. Okay? When we ask you for the distance, you might tell us that we moved 4 feet to the left, but when I just ask for the distance, I just want to know 4. Okay? If your total distance, if you're looking for total distance, remember, the total distance will be the same as the net distance if you never change direction. However, if you change direction, then you must calculate about that turning point. Let me give you an example that I like to use for for students. So I have teenagers. My teenagers drive, right? So let's say we're practicing in my driveway and my teenager is practicing backing up and pulling forward. Okay? So if she gets in the car and she backs up the length of my driveway and then she pulls forward back to her original starting point, her net distance is 0. Beginning point minus ending point would be 0 because she ended and started and ended in the same place. But if we look for total distance, her total distance is the length of my driveway plus the length of my driveway. It's the difference between total distance. I have to take into account that she changed directions when I calculate that total distance. Let's look at some examples, but don't forget, you can always pause and get the notes down so that you make sure you know the difference between total distance and net distance. For this problem, we're given the position function. We want to find the net and total distance from 1.5 to 4 seconds. So let's do the net distance. I always think that's the easiest one because we do the position, we subtract the positions. Those are pretty easy. I'm going to put this one in my calculator. I'm going to switch my view so we can all see my calculator. I have a graph still on there, so let's just go to y equals. I'm going to clear it out, and I'm going to put my new position in here. 2x cubed, oops, and let me come out of that exponent, minus a 6x squared plus 8x, okay? Oops, I got two x's in there. There we go. And I'm just going to graph on a Zoom 6 window, standard window. Because I want the value of this when t is 4 or when x is 4. Don't worry that it's going off my graph. That's going to be okay. Second trace number 1, and we want to put in 4. Notice that my position is 64. And let's do the position. So second trace value number 1, put in 1.5. And that's at 5.25. So I get 58.75. That is my total distance. All right, now I have to check and see sorry, that is my net distance. Now before I do total distance, I have to check and see if this changes signs, if this changes direction. And the way I do that is to set the velocity equal to 0. First, I have to find the velocity. Okay, now I'm going to set it equal to 0. It looks like this all divide by 2, so I'll factor out a 2. Okay, that's not going to factor, so let's go with my calculator. I'm just going to go into y equals. I'm going to turn the function off by highlighting the equal sign and pressing enter. And then I'm going to type in the velocity into the second equation, y2. And I'm going to graph this. Remember, I'm only looking between 1.5 and 4. I need to know if the velocity changes signs. And it doesn't. Notice the velocity stays positive the whole time. So my total distance will be the same as my net distance because velocity was always positive on that interval. Okay, but you have to check. You can't assume that the object did not change direction. You have to go check and make sure. Okay, let's look at a couple more examples. So our first one, we're told the position function, and we're looking for the net and total distance. And again, I'm going to do the net because I think it's probably the easiest. It's that you can do it either way. If you want to do beginning position minus ending position, or you want to do it vice versa, it won't matter because you're going to do the absolute value anyways. So let me clear out these two functions quickly. And I'm going to put in the position. So I'm doing e to the 2x minus 8t. And then I'm going to do my values, right? Second trace, option number 1. Second trace, option 1. Let's put in 0.5. And that I get 1.282. And then I'll do the same thing. Second trace, option number 1. And this time I'm putting in 1.5. And I get 8.086. Now you can do the subtraction there. I'm going to do it pretty quickly on my 4 function. And I get 6.804. All right, now let's check the velocity again for this one. The derivative would be 2e to the 2t minus 8. Again, in my calculator, I'm going to turn the function off, and I'm going to go to the y2 and put the derivative in. And then I'm going to see if it changes signs. Remember, I'm only concerned with between 0.5 and 1.5. I just need to know on that interval, does it change signs? And look at it, it does. Okay, so we're going to have to split this up. I'm going to use the calculator to find that value. Okay, actually, let's just go ahead and I'll move the 8 and divide by 2. And then you can take the logarithm and divide by 2. And that value that I get there is 0.693. Okay. So I know it changes position, it changes direction there. So to do my total distance, watch the subtraction that I have to do. I have to do the position between 0.5 and 0.693, right? From the beginning to the turn. And then I have to do from the turn to the end. Okay, now the good news is I have some of these values already. Remember, I have already found the position at at 0.5. Okay, so now I'm going back into my calculator. I'm going to turn off the derivative, turn back on the function, and I need to find the position at 0.693. So it's second trace option number 1 at 0.693. And notice it's negative, so you do have to include that negative. 1.545 plus, then I've got negative 1.545 minus the position at 1.5, which was 8.086. Okay, so go ahead and do your subtractions there. I'm just doing sorry about that, on a 4 function. It's a little bit faster. Okay, and then I've got 9.631. And remember, this is after you take your absolute values. That gives you, that gives you a total distance of 12.458. Okay, but the point is, notice with the total distance, I have to do the distance from the start to the turn, from the turn to the finish, and make sure I use absolute values on both of those. All right, one more problem for this set here. We're being given the position and we're looking for that net distance and that total distance as well. So let's take a look at net distance. Again, I think it's the easy one. So I'm going to do the position at the beginning minus the position at the end. So pi over 6. So I've got position there is going to be pi over 6 plus 2 times 1/2. If you need to draw your reference triangles to do that trig, please do. Minus, and then I've got 5 pi over 4 plus 2 times negative square root of 2 over 2. So I've got pi over 6 plus 1 minus 5 pi over 4. Distribute a minus, that's going to give me plus square root of 2. That is not going to be a very pretty number, but is totally okay. We will get a decimal if you want to put that in your calculator, 0.989. All right, next for the total distance, I'm going to use the calculator. So I'm going to go ahead and take the derivative, which would be 1 plus 2 cosine. And I need to know if that changes signs on this interval. So let me clear out these functions. I'm going to put in 1 plus 2 cosine x. Let me look at just this interval. So I'm going to put in pi over 6. And I'm going to put in 5 pi over 4. That is not what I wanted there. Pi over 4. There we go. So we're only looking at this interval. I just need to know if the velocity changes signs, and it does. So we'll use the zero method here. Second, trace number 2. We're going to find that value, or have the calculator find that value. So move to the left of where you see it crossing the x-axis, press enter. Then move to the right of where you see it crossing the x-axis and press enter again. Press enter one more time, and you see we get 2.094. Now, to do our total distance, remember, we're going to have to calculate the distances about the turn. So we're going to do the distance from pi over 6 to the turn. And then we'll do the distance from the turn to 5 pi over 4. Now, just for time's sake, I'm not going to show putting these in because you can do that on the calculator. You can put the position in the graphing calculator, do your values, but check, you should get 3.617, and it's in feet because we were given units here. So I'll go ahead and label that. I hope this helps with the difference between total distance and net distance. It's very much a distinction you need to know for the AP exam. We all know particle motion's probably going to be one of the 6 free response questions, and so you want to be prepared for it. I will link my 5 commandments of particle motion video below, because if you haven't seen it, it's one you definitely want to have fresh in your mind when you get ready for the exam. But if you have questions or anything I can help with, please feel free to leave a comment below. I would love the opportunity to do that. Also, don't forget to like and subscribe. Thanks for watching. Bye for now.